Uh, okay, welcome to my super professional, legitimate, original lecture on electrical engineering to explain what the hell we're actually meant to be doing for this lab report because we've been given no guidance whatsoever. Okay, what are we actually doing in this lab report? The whole point of this is that we're going to try and get an Arduino. We're going to stick a thermometer into it, get a thermistor, which is like a type of resistor that varies depending on the resistance varies depending on temperature, and put it in a thing called a voltage divider. I'll explain what that is in a second. We're going to write some code on the Arduino. We're going to be able to read the temperature off of the thermometer, and we're going to be able to read the voltage value on the thermistor. And then roughly from that, we're going to be able to calibrate the thermistor so that we can have it also roughly tell the temperature. Because the thermistor's whole point of a thermistor is that the resistance of this will change depending on what the temperature is. So if we know what the temperature is, we can roughly calibrate its resistance and figure out, like, have this also tell us the temperature. Okay, so great. But what the hell actually is an Arduino? An Arduino is pretty much like a miniature computer. It's the best way of thinking of it anyway. Instead of being a computer that runs an actual operating system or displays to a screen or anything like that, it runs really, really low power basic applications, basic scripts that we can write and upload to this thing here, this circuit board here. This is what the Arduino is. It's called a microcontroller. If you look for them online, you'll often see them called MCUs, which stands for microcontroller unit. The Arduino is by far and away the most popular and well-known one, but there's loads others. The ESP32 is pretty new and high-tech. The STM32 is like a slightly more powerful version of the Arduino. There's loads of different types of Arduinos. The ones we're using are the Uno, but there's also the Micro, the Nano, the Mega, and then a load of like weird niche ones. A Raspberry Pi is also sometimes referred to as a microcontroller, but a Raspberry Pi is more a computer. Raspberry Pis actually run an operating system. You can like download Google and watch YouTube videos on a Raspberry Pi. You cannot in a million years do that on an Arduino. There's also Texas Instruments made one a while ago called the Launchpad. It was terrible, awful. Please, for the love of God, never use it. And then there's a bunch of like weird niche ones that are way too beyond the scope of this, but they're out there. Microcontrollers are great because they let us run whatever mini program or thing any program, any script, anything that we want, which is great when we want to interact with electronics because these things are really cheap. So you can afford to mess around with them and break them way more than you could if you tried to connect the temperature probe to your computer and you accidentally broke your computer. That would be a much more expensive mistake. Breaking this is like €5. So, yeah, that's what they're used for. They're also used by actual engineers in the real world doing actual stuff to test and demo circuits before they order more advanced circuits or like order the product version of whatever they're developing is. They're really good for like rapid prototyping. Okay, this is probably a bit over the top of an explanation. But this stuff is what I find really interesting, so I'm going to really quickly explain it to you. How does the Arduino actually work? Like, how does it actually work? Well, there's three like main sections that we can divide this into. There's this over here, which is okay, that is not working. Okay, technical difficulties, sorry about that. So the way that this Arduino works, you can break it up pretty much into 3-4 different segments, okay? You have the actual USB cable, which is mainly these components here. You have the Arduino computer itself, which is mainly these components here. And then you just have power, which is like this stuff here. And then the fourth arguable component is like the I/O, which is these headers up here, and then also these headers down here. These are called headers. They're just the areas that you stick the pokey things into. How an Arduino actually works is this right here, this component right here. Blue is not a good color for that. This component, that is a terrible red. This component right here is the actual Arduino chip. It's called the ATmega328P. that you don't need to know any of this for the lab report. I'm just explaining this because I feel like it's actually quite hard to get an explanation of this online. The ATmega328P is the actual computer that is running the code in your Arduino setup. When you write the code and upload it, this is the thing that's processing it. When you have your computer, you connect it with USB to your computer. The USB comes in here through this port. It then goes to this chip here. This chip is, what it will do is it will take the USB data from your computer and it will translate it into a thing called UART. The best way of explaining what that is that USB is a communication protocol for ones and zeros, like binary. I'm going to lower my brush size slightly. For ones and zeros, like binary. And so is UART. UART is also for ones and zeros, like binary. So on paper or physically, they're identical. But the difference between them is that USB contains data which is only necessary for some USB devices, like, I don't know, a storage device or a keyboard or a mouse. There's data in USB that an Arduino, for instance, doesn't need. The Arduino only needs the UART data. So you can, this chip, what it will do is it will take the binary ones and zeros, the electrons coming from your computer, in the USB format, and translate them over to a UART format, which the Arduino can then read and can be programmed with. A good way of thinking about it, alternatively, if that went over your head, is your computer is speaking in like double Dutch complicated French, and the Arduino only needs caveman speak. It only needs to know like really basic American English. So this chip here is going to take the really complicated language the computer's talking in and dumb it down to a really basic language that the Arduino can be programmed with. That's the point of it. What happens then is you upload your code, you flash it, it goes to the Arduino. The Arduino here, that is actually what's running your code, that'll run your program. And the USB from your computer also goes into these components here, which is just like capacitors, regulators, stuff we'll learn in actual electrical engineering. And that is what's responsible for powering the Arduino and also for giving power to like the 5 volt and ground rails that are on the various areas on the board, like ground over here, 5 volt here, ground here, etc. Like all the power and ground comes through the USB and it goes through these components here. So, yeah. To be clear, that explanation I gave is way more than we'll actually need for the lab report. I just think that it's good to have an understanding of an Arduino of that scale. If that went over your head, don't worry about it. We'll be going over this in later years in college. Now, I also want to just quickly explain how breadboards work. The breadboard that we've been given with in the little box isn't connected to the Arduino at all. Breadboards are really useful because what they let you do is they let you connect a bunch of different things together however you want and test and prototype with them without needing to solder them together or wire them together or make a circuit board or anything like that. You can just stick a load of wires in a breadboard and connect things. How they work is you have rails on the side here, and then you have these things in the middle, all the little dots in the middle. Each one of these areas, these rails electrically are connected to each other vertically. So all of these pins right here are all connected vertically. They're all conductive with each other. They're colored red and blue. It doesn't actually matter what you put in them. They're colored red and blue just because most people use them for power and ground, where red is the plus power and blue is the ground, purely because power and ground is just a very common thing that you want to have in a circuit. So they have way more pins for power and ground so that you have loads of area to access them. Then the actual horizontal bits here are all connected with each other horizontally, but not vertically. So you can see over here, you can see the metal strips. This is the underside of the same breadboard. They're all connected horizontally with each other in rows, but not vertically. They don't share any connections vertically. So when you want to connect different things in a breadboard, you want to use a breadboard, it pretty much lay things out according to that. Lay the things you want to connect with each other in the same row. Lay things that you don't want to be conductive with each other. You can bridge to different rows. So if I wanted to connect, we go say like power goes over here, and then we have ground come up here, and then some other component like a light bulb I have, let's say over here. I can connect the power rail of the light bulb here, and I can connect the ground rail of the light bulb over here. And now these two aren't touching each other, they're not conductive, they have to go through the light bulb to be powered. That's how breadboards work. Just an explanation, because that also wasn't explained to us. Okay, so let's connect the temperature thing that we have earlier to the Arduino. The temperature probe itself is called the LM35. It's made by Texas Instruments, and it's a calibrated thing that will actually give you a very good reading of the temperature if you connect it properly to the Arduino, which is why we're using it as like our reference thermometer, for lack of a better term. This is telling us the actual temperature, so we're using it as a reference to calibrate our thermistor with. If you read the datasheet of this thing, which I don't recommend you do because it's, well, no, you should, honestly. It helps explain some other stuff, but it's really complicated and it's like 35 pages long. But the main things you need to take away from it are that it needs between 4 to 20 volts of power in. So what that means for us is that we have 5 volts right here on the Arduino. So the VS pin, otherwise known as the voltage source pin, gets connected to the 5 volts on the Arduino. Cool. Then we also need to connect it to ground. So we'll just connect this symbol here to ground. Oh yeah, if you ever see this symbol, by the way, if you haven't done physics, that's the symbol for ground. That's just the electrical symbol for what ground is on a circuit. Cool. And now finally what we're going to do is we're going to connect the signal pin, which is S, to any of the analog pins on the Arduino. Now, the analog pins are here. There's 6 of them, analog 0 all the way through analog 5, or A0 through A5. The reason we connect it to an analog pin is because a digital pin can only take what's known as a digital input, which means pretty much 0 or 1, on or off, low voltage, so 0 volts, or high voltage, so like 3 volts or 5 volts or whatever. It just is on or off. It's a switch, it's a button, it's a laser trip, it's something that is, like, it only can exist in 2 states. That's what a digital input is. But this thermometer here is actually going to output a variable thing. So the thermometer here is going to output between 0 volts and it's going to output roughly between 0 volts up to, if memory serves correct, it's like 1.5 volts or something. So if you plug that into a digital pin, it's not going to work. You need it to be into an analog pin. An analog pin can actually read this and then interpret it as a specific number. In the Arduino's case, it will use a thing called an analog to digital converter, which is, for now, just take it as a magical black box. It's beyond the scope of this. We'll learn how they work in later years in college, I think, if any of you do any electrical modules. But analog to digital converter, an ADC, that takes the voltage that's outputted from the thermistor, plugs it into the Arduino, and then it's going to spit out a number in binary that starts at 0 and goes all the way up to 1023. There's 1024 values, but it goes up to 1023 because computers start counting at 0, which is also extremely confusing. But yeah, just deal with it. There have been rocket crashes over people mistaking computers starting at 0 and 1. So yeah, don't worry, everyone makes the mistake. Now this special property of going from 0 to 1023, that is only available on the analog pins on the Arduino. There's only a limited number of these pins because it's more complicated to do this. So the actual silicon chip can only handle so many analog inputs. So it doesn't matter which one you use. We just need to use any of these 5, and then yeah, we'll get a value between 0 and 1023. So what does this look like when we actually code it? We can do that right now. When you open up, this is the Arduino IDE, by the way. This might look different from what you guys were using in the lab because this is the most up-to-date version of it, which is like a really nice dark theme. I recommend you get it on your computers. You can download it on their website. It's super easy to download. It's just one application, and then you just hit yes to a load of questions, and it will dump you into something that looks like this. I'm gonna write a really basic example code for how we're actually gonna interact with this thermometer. So, okay, first thing we want to do is we want to write serial.begin 9600. Why are we writing serial begin 9600? Because this confused me. Serial means the Arduino is sending data serially. Serially means one after the other, after the other, after the other. It's like fancy English for no reason, but it literally means it's just sending a binary bit after another binary bit after another binary bit in a serial sequence on and on and on forever. So that's why it's called serial. We're telling the Arduino to start doing that when we say begin, and then we're using this number here, 9600, which means that it is using a baud rate of 9600 bits per second. So the baud rate means the number of binary bits it sends per second. In this case, it's 9600. The reason it's 9600 doesn't matter. Who cares? Just use 9600 specifically. There's a few different values you can use for different reasons. It doesn't matter. It's just 9600 works. Now, what I'm going to also do is I'm going to do what they put in their lab report. If you are reading the lab report and you're confused about this, don't worry. I'm going to just say analog reference external, because this is in their example code and they don't explain why. So I'm assuming this won't cause any issues whatsoever. There's no way that this could possibly make the code not work. Cool. Now we go into void loop. What we just did there is void setup. This code runs once when the Arduino boots. So when the Arduino turns on, it will run these two lines of code. And then after they're done executing, it will move down the instructions. Also, all code, if you've never ever written code, it will execute down in a straight line, like 1, 2, 3, 4. It will execute code in the order you've written it in. So that's just something to watch out for. Void setup will finish. It'll then head into void loop. Void loop, how void loop works is it'll go 1, 2, 3, 4, whatever. When it gets to the bottom of the very end of the loop, it just goes back up to the top and does it again. It just loops over and over and over again. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, till the end of time, until you unplug the Arduino. That's how void loop works. What we're going to go in here is we're going to say, okay, we're going to say reading. Reading is just the word that we're using for what we've read from our thermometer is equal to analog read. Yeah, I spelled that right, yeah. And then A0. Why am I using A0? Because if you go back here, I connected the thermometer to the pin A0. If I connected it to A3, then in the code I would write A3. I'm just using A0 because that is the specific use case that I've had. Okay, if you try and compile this, it'll give you an error. The reason it gives you an error is because you actually, when you're programming, you need to tell the computer what things are. So reading in this case is a number. It's going to be an integer number. An integer number is a number that isn't a decimal. It's a whole number. You need to tell the computer that. Otherwise, the Arduino, it doesn't know what to make this in memory. It doesn't know how to define this. So I'm going to say int. Int is shorthand for integer. We're basically telling the Arduino, okay, reading is an integer. The integer is going to be equal to whatever you read on the pin A0, whatever you've read from the analog pin A0. Cool. Now I'm going to say serial.println reading. What this will do is the Arduino will take the number of whatever reading is, could be anything between 0 and 1023, and it will actually write it back here in this console where all this red text is. It'll write it in the computer. The reason you say println is because if you wrote print, it'll print a straight line going on forever and ever and ever to the side. ln means when it's done printing, it'll hit enter for you. It'll like move to a new line. That's what the ln is for. And then I'm going to say delay We'll go 100. So that means it'll now stop for 100 milliseconds. Cool. The reason I'm also doing that is because if I didn't do that, then the Arduino would print this roughly 13 million times every second, which is a lot. We don't really need that, so we're just going to tell it to wait and slow down a little bit. So the delay 100 is just literally just so that it's not doing it 13 million times a second. Cool. So this also won't work because I'm silly and I forgot to do one other thing, which is that you need to go up here and you need to type in pin mode A0 input. The reason you're doing that is because you specifically need to tell the Arduino that the A0 pin is going to be an input pin. It's going to be taking data in, it's not going to be spitting data out. It's important for the Arduino to know that because otherwise it will just ignore it if you try and put voltage in on that pin. Specifically why, again, just take it for granted you need to do that. You need to let the Arduino know why. There's explanations for that you can find online if you're curious not to research it. Okay, cool. So I don't have the Arduino plugged in right now, but if you ran this, then you would expect to see the thermometer temperature printing, except, oh wait, no, you wouldn't. You just see 1023 like this in the serial line over and over and over again. It would just be printing this data over and over and over again like this forever and ever and ever and ever and ever, which is not great. Why is that happening? Okay, so the reason why they have that line here in the lab report, the analog reference external, is because they want you to use the analog reference voltage of 3.3 volts. What the hell does that mean? Remember earlier when I said that the Arduino is the temperature probe on the Arduino is outputting between roughly 0 to 1.5 volts? Well, the Arduino is going to take that and convert it to 1023. But the problem is, how does it know that 1.5 volts is the highest value? It actually doesn't. So by default, the Arduino will map 0 from 1023 between 0 volts up to 5 volts. Because 5 volts is the internal, it's the internal voltage the Arduino uses, it's the logic the Arduino uses. So it's just going to operate off of 5 volts. So what that means is, if the signal on the pin is 0 volts, then it'll output 0. If it's 2.5 volts, it'll read that as roughly 512. And if it's 5 volts, then it will read that as 1023, which is the highest value. Cool. But what you've gone and done is you've said, okay, no, I want the reference voltage to actually be external. So that means that the Arduino is going to be looking for a voltage on this pin here, A ref, where A ref is going to be that reference voltage. You define what that reference voltage is. So you're telling it, okay, don't actually map between 0 and 5 volts. Map between 0 and A ref. So what we're going to do is we're going to map it between 0 and 3 volts. Why are we going to do that? Because it's more precise. Because this only actually goes between 0 volts to 1.5 volts. If we're measuring between 0 up to 3, then this has more ranges, there's more value, there's more data where this is valid. Because once this goes beyond 1.5, or once the 3 volts goes beyond 1.5, that's not going to matter, because this thermometer is only ever going to output a max of 1.5 volts. The Arduino won't be able to read, or it's not going to output more than that. So if our reference voltage is between 0 volts all the way up to 5 volts, there's only a really small band of the possible numbers here that's valid for the thermometer. Whereas when it's between 0 and 3 volts, more of the numbers that the Arduino could output are actually going to be output, if that makes sense. That means it's a greater resolution that the Arduino can read in, which is good for us because it's more accurate. So that's why we're doing it. But what we need to do in order for that to work is we need to specifically go and say that the 3.3 volt pin here, the 3.3 volt here, this pin here, is connected into a ref. Because if it isn't connected into a ref, then a ref doesn't have any voltage on it. So the Arduino is reading between 0 volts to 0 volts, which is great. So the thermometer is outputting 0.1 volts. And wouldn't you know it, 0.1 volts is greater in value than 0 volts. So the Arduino is just stuck constantly outputting the highest value. And oh wait, that makes sense. Okay, so that's why the Arduino was constantly outputting 1023. Because it was reading 0.1 volts. It's just 0.1 volts is higher than 0 volts. And I picked 0.1 volts because that's like, it's an arbitrary number, but the thermometer will output some voltage for the temperature. It doesn't really matter what it is. It'll output some voltage, and any voltage is going to be greater than 0 volts. So the Arduino is always going to output 1023. It'll always output the highest number. So that's specifically why we've set a ref. It has to be 3.3 volts, because we're telling the Arduino, okay, you're going between 0 volts. You're measuring between 0 volts up until 3 volts. You have to do that. If we didn't do that, it would default at 5, but that's less accurate. Okay, cool. So if we do that and we come back in, everything here should work. So if we, specifically what I mean by do that is if we go ahead and connect 3.3 volts up to a ref, like so, then this line of code right here will actually do what it's supposed to. The Arduino should then output, what I was getting was roughly about 70, 71-ish for room temperature. I've seen other people get that as well. It should be in and around that range. That's the rough range that we're going to be using. That's just the number that the thermometer works at room temperature. It's just 70 is what it outputs at room temperature. Okay? Cool. Also, I'm so sorry, this is getting way longer than I actually wanted it to be, but whatever. Okay, right. So now we're going to hook up the thermistor to the Arduino, and we're going to do that very similar to the original thing, but really quickly, the lab report guy said, oh, let's do it with a voltage divider. Why are we doing it with a voltage divider? What even is a voltage divider? Okay. If I have, we'll say, 5 volts in here, and I connect it to a resistor, we'll say 10 kilo ohm resistor. Also, a square is the universal symbol for a resistor. We'll just say 10K for 10 kilo ohm, right here. 10 kilo ohm. And we have that going to ground. Cool. This doesn't really do anything for us. It just resists current. The 5 volts specifically, and the ground is just resisting an amount of voltage, and it's going to ground. But what's important here is that there is a thing that we'll also cover if you do electronics called Kirchhoff's law. Kirchhoff's law states that all of the components in a circuit, so in this case the 10 kilo ohm resistor, must consume all of the supplied voltage to that current, the 5 volts. So that means that this 10 kilo ohm resistor is responsible for dealing with 5 volts of power. That's great, and it means that if we stick a voltmeter over our 10 kilo ohm resistor, we'll measure 5 volts on the voltmeter, because it is specifically dealing with 5 volts of power. Okay, cool. Why does this matter? Well, this matters because if we instead, let's say, had our thermistor on this line, the symbol for a thermistor looks like this. That's just the symbol for a thermistor. There's a really weird explanation as to why, but just, yeah, that's the symbol. If we have the thermistor, this is cool. The thermistor, the resistance of this is going to change. So the value of this, when it's at room temperature, it might be 1,000 ohms. It might be 1 kilo ohm. But when it's at 100 degrees, maybe it's 5 kilo ohms. Maybe it goes up. Okay, cool. So that's great and all. So let's measure it. Let's stick a voltmeter across it. And, oh wait, hang on. We just read 5 volts. It doesn't matter what the temperature is. It doesn't matter how much the resistance changes. 5 volts is still growing across this thermistor. So, okay, that's great. How do we read it then? How we actually are meant to, how we can theoretically read it is we can use what's called a voltage divider. What a voltage divider is it takes advantage of Kirchhoff's law. If we have a 10 kilo ohm resistor here in our circuit, and then in series with it, we put a thermistor, and then we connect it to ground like so. Something changes. Now, if it's if it's, let's say, 20 degrees, it's room temperature, it is 1 kilo ohm resistor, yeah? But if it's 100 degrees, then it's a 5 kilo ohm resistor. These numbers are just arbitrary, by the way. It could be the other way around. It doesn't really matter. It's a, explanation. It doesn't matter. If we measure the voltage across the circuit with a voltmeter, it'll equal to 5 volts. But something really interesting happens if we now measure the voltage specifically over the thermistor. Now, if we measure it, the voltage will change. It'll be an arbitrary value. These also these numbers don't matter. I'm just giving this as an example. Now, the thermistor will be a different voltage value depending on the temperature. So what happened? Why is the thermistor now a different voltage value? Why? Also, these volts aren't correct. I'm just saying it will be different. It'll be different by a mathematical formula, which I'll show you now in a second. But this is just an example. But they're different at temperature. Why is that? Well, the reason why that is because if we remember from earlier, what I said is that Kirchhoff's law states that all of the components need to consume the voltage in the circuit that's being supplied. In this case, 5 volts is being supplied, and it's going to ground. That means that this and this need to consume 5 volts together. So in total, 5 volts is being consumed by both of these. However, when the temperature is 1 kilo ohm, then this resistor here is 90% of the resistance of the circuit, which means that it's more than likely consuming about 4.5 volts, 4.6 volts. It's consuming most of the voltage, and this, in comparatively, is consuming very little. It's consuming like 0.4 volts. Because in total, this must sum up together in total. These values must sum up together in total, so that the entire voltage consumed is 5 volts. But the voltage consumed is going to be proportional to the resistance of the component. So when the temperature goes up, and the thermistor is not 1 kilo ohm anymore, it's now 5 kilo ohms, the total resistance of the circuit is 15 kilo ohms, but this resistor here isn't 90% of the resistance anymore. Now it's 2/3 of the resistance, which means that now it's only going to be consuming about 3.33 volts, or we'll say the 3 volts across this. Something within that range. It's like roughly this voltage. And that means that the resistor must be the thermistor must now be consuming more of the voltage. It must be responsible for the entire 5 volts to get consumed. So now this thermistor must be consuming, we'll say, roughly 2 volts. So that means that in total, 5 volts is still being consumed. However, and if we were to read across this point here and this point here with a voltmeter, we would see 5 volts go across this line. But what's really important is if we read a voltmeter across this and across this, then the value voltage it reads here, the value voltage it sees, is going to change as the resistor value changes, which means it's going to change as the temperature changes. And that will remain constant for the circuit no matter what, which is really important, and that is how a voltage divider works, and that's why we're doing this. So now, I'm sorry, this explanation is very long-winded, but finally, let's connect the thermistor in a voltage divider to the Arduino. I stole this diagram from the lab report. Don't be scared by it. This is still the exact same. RS is still our resistor from earlier. The one we're using in the experiment is 10K. It doesn't really matter. 10K is just a pretty standard one because of other electronics reasons. But it doesn't really matter what we use. It just matters that there is another resistor so that we can make a voltage divider. What we're going to do, we're going to take 3.3 volts specifically. That is going to come over here and it's going to jack into VS. VS stands for voltage source. Then we're going to take ground. We're going to hook that up to the end of the thermistor. So the thermistor is going to go, the resistor 1 is going to connect to power. The other end of it is going to connect to the thermistor. The other end of the thermistor is going to connect to ground. And now specifically the bridge where the resistor and the thermistor connects, we're going to connect a third wire. This will be our signal wire. This wire will be the equivalent of our voltmeter. It will be measuring the voltage across the thermistor in our resistor loop. The voltage on this wire, the V out, the voltage on this wire is going to change depending on the ohm resistance of this thermistor because of the explanation I made earlier. So this wire now is going to have a variable voltage. So it's going to be between 0 volts up to some arbitrary value. I don't know. Well, actually, no, it won't really be. It'll be between like 1-ish volts when it's freezing cold all the way up to some other voltage as well. Like it will be between 0 and 3.3 volts, but it doesn't matter. It will be variable, which is really good because now what we can do is we can stick that into A1. I'm going to use A1 because we already used A0 for the thermometer earlier. And now that is it hooked up. That's it ready to go. In the Arduino code, all we would need to do is change this to A1, this variable that I have here, to A1. And if we started reading this, if we ran this code and started reading it, you get a value, for me it was roughly 500. It might be something else for you. I got around 500. You might get something else different coming through on the serial monitor. There you go. Now you're reading the thermistor. So based on my explanation, you now should have code that works for reading the thermistor. You should have code for reading the thermometer. You should be able to read both of them and have them both printing out to the computer code terminal. Grand. So the actual experiment, the write-up that we're doing, I hope now is a bit more self-explanatory. We're going to make a circuit and code that can read the thermistor. We're going to make, I've explained that. We're going to make a circuit and code that can read the thermometer. I've also explained that. We're going to confirm that with the multimeter. We have been given guidance on how to use the multimeter already. If you guys don't know how the multimeter works, I'll also make a very short video showing how a multimeter works. But pretty much the value the Arduino is reading, you should be able to do some maths to convert that into a voltage. I'm not going to walk through that maths now because it's very basic and this video is 40 minutes long. But like, put your thinking cap on. If it maps a voltage value between 0 and 3 volts to a value of 0 and 1023, how would you reverse engineer a voltage back out of that equation? Like if it was between 0 and 5 volts and it gave you 500, you'd know it's roughly 2.5 volts. Apply the same logic to this and make a formula for it. You then compare the voltage that you're recording based off the multimeter. That's cool. That's part of what you need to do for your write-up for your experiment. Then calibrate the thermistor using the thermometer. What you need to do is, with the breadboard, nudge, nudge, wink, wink, hook up a thermistor and a thermometer to the same Arduino at the same time and write code that can read both of them. Nudge, nudge, wink, wink. All you really should need to do is that and make a second one of these. I'm not going to go through all of this because at that stage I'm risking, I don't know if they're going to care about plagiarism. but just make code that can read both of them at the same time. It's the equivalent of just duplicating what you have already. And what you need to do to calibrate it is literally get the thermometer in your hands and go, okay, room temperature is roughly 25 degrees Celsius. Cool. The thermistor is now roughly at 25 degrees Celsius. Cool. Now put them both in your hand and take it as roughly, oh yeah, it's about 35 degrees Celsius in my hand. Cool. Great. So now the thermistor is at 35 degrees Celsius. The change in the values that I read between these two is a difference of 10 degrees Celsius. That's its calibration done. That's all you need to do. That is the most basic way you can calibrate it. You can also do some other more complicated stuff to calibrate it better if you want, which I've done, but I'm not going to explain all of that because of plagiarism, but you can have a think. Potentially one way of doing it might be to, I don't know, measure something of a really well-known temperature, like freezing water or boiling water. That could be a way of getting a more accurate reading, for instance. Then in your lab report, all you need to be able to say is that you have a rough idea of the thermistor's resistance compared to the temperature in the room, and write that up, and that's the lab report done. That's the lab, that's what we're doing, that's everything being explained. If there's any further questions, if I've explained anything poorly, then please let me know, and I'll add a voice note, or I'll send some messages in or whatever. And the final thing, and then you can go and watch Netflix and do whatever else, is the thermometer that we've been given, the LM thing. This has not been told to us. It's really important. Oh God, what am I doing? Here, I'll just write this out. It's really important. That thermometer, I'll double check the datasheet. If this is wrong, I'll send a message in saying it's wrong. It outputs 10 millivolts, or 0.01 volts, per degrees Celsius. So if you're reading 70 on the Arduino, then 70 is going to be somewhere between 0 volts and 3 volts. So we'll say 70 is there. Okay, cool. That means you need to convert this 70 into a voltage value. So I don't know, let's hypothetically say it's like 0.5 volts, cool. 0.5 volts. 0.5 volts is going to be 50 millivolts. Or no, it'll be 500 millivolts, I'm sorry. If it's 1 degree for every 10 millivolts, then that means that this is 50 degrees Celsius. Now that's really high, but yeah, so room temperature will be like a really low voltage. Room temperature will probably be like 0.2 volts or something like that, a lower voltage for roughly 20 degrees. But that's how you can convert the voltage that you're reading off of the thermistor, the temperature probe, to an actual degrees of temperature. Just watch out again between 0 and 3 volts because of the analog reference voltage thing we did. If we do between 0 and 5 volts, then you've got to do your math between 0 and 5 volts. That's the only thing. Okay, that's everything explained. That should be all good. Yeah. I hope this was useful and not way too long and explaining and yeah, whatever. Enjoy your evening. See ya.